All right. So yeah, there is two people, right? Yes, Aryan. Do you have any doubts in the slides, in specific one? Week four. Yes. Okay. Oh no, that was before. Sorry. Yeah, no doubts, is it? Great. Okay, I'll just go through the slides then. Uh, so yeah, so we stopped week three at policy iteration, where we first took any. So the idea was that there is a partial ordering in your policies, which is given here, and sorry, it's way behind. Yes. Yeah, here. Yeah, policies can be partially ordered, which means whatever sort of relation is greater than or equal to you're defining is defined for some pairs. And yeah, so here the ordering is basically the value function value being greater for all s in your state space. And we discussed a strategy where whenever when I input when I give you any policy, by performing policy improvement, you can get a policy that is for sure better than the current policy. And that policy, at least the way we obtained it, was a deterministic policy. So we will find for any given policy a deterministic policy that is as good, if not better, than the initial policy. So that was policy improvement. And then uh, we keep we first, yeah, we improve the policy, then evaluate the value function of that policy, then improve it again, and so on. And that became policy iteration. The idea in value iteration is to interleave these at a much more granular level. So if you recall in policy, yeah, if you recall in policy evaluation, the what we are expected to do is to solve a system of simultaneous linear equations, right? But in policy evaluation, we came up with this iterative approach, where just instead of solving it, if you do this iterative algorithm of just keeping on reassigning the right hand side back, by the right hand side being this part, if you keep assigning the right hand part to the to vs, if you keep doing that, the idea is that after some point the value function will stabilize. So this is instead of solving a system of equations. Once we do that, then we go to improvement, where we get this new deterministic policy, right? And then we keep evaluating. What we do in value iteration is we don't necessarily complete do complete policy evaluation and then complete policy improvement. We make the optimality equation itself into an update loop. So this is how it is, right? So instead of saying first evaluate policy, then do so, the way we are doing it is we are taking the max over this action, which we did before, which was the optimality condition, and then we iterate along in this fashion. So that's value iteration. The algorithm is basically just that: set the threshold, initialize, then do the max here itself. You're doing both. Uh, this doing this, the idea is that uh, doing this does both evaluation and iteration in one shot. Evaluation here, and then the sort of the max condition is this. So let me mark that as well. So this is improvement, and then this is evaluation. Yeah, so we are interleaving that in just one go. This as usual is just to keep track of the stability, if it has not changed as much. And then you just output, yeah, you output a deterministic policy though. So recall that there can be multiple, so there are multiple, so the relation between a value function and its policy is not one to one. You can have many policies that share the same value function, and it so happens even there can exist multiple optimal value functions as well. But yeah, so in this case, at least we find a deterministic optimal policy function. That's value iteration. And yeah, this is just applying those things. And examples. Then we have asynchronous DP. So here the disadvantage is we do not do updates over the entire state set. In synchronous DP, the updates are not done over the entire state set. Have to ensure that every state is visited. So when does this happen? When you kind of roll out some policy from a certain state, when you follow that policy, you are only going through certain states. There could be certain states in your state space that is very rare to visit, right? So you don't go over there, but that still works. So you can still, using asynchronous DP, you can only focus on parts of the state space that is relevant to the problem. And when you do that, it's just that you need to ensure that all the states, as given here, all the states are visited sufficiently so that the value function actually converges. That's asynchronous.
So
And
here
in
just
real time, yeah.
When you are actually follow this means value iteration with taking the maximum, means Bellman optimality equation, somewhere you are actually for moving forward with a greedy approach, right?
Correct. Yeah. Greedy, no? So at that stage, you're saying with the
This is
evaluation, the max part, right?
best possible way I should move.
Yeah. Okay. This part, the max part. That's what you.
Yeah.
Okay.
But in the lecture also, sir said you go to that asynchronous DP page.
Okay.
Yeah. If you look in the top left corner, sir, actually draw this diagram.
Okay.
If you when you start from the source and you are moving to a goal, somewhere you are following this diagonal path to move to that goal, because that is the way the best Bellman optimal equation will take you from the source to goal.
Okay.
All the alternative path where in this particular scenario there are many Bellman equation optimal path may exist, but all the paths fall under this zone, this diagonal zone. That is why, sir, draw that band.
Okay.
Now the question is, as you said, before going to the next step, you are ensuring that all the grid point will be visited sufficiently.
Yeah.
How you ensure the corner of the two left and rightmost corner is visited sufficiently?
Right. Yes. So if the thing is that is just for convergence, and the way you could do that is to arbitrarily start your agent from a certain spot. Like here we have fixed, so that is one way. I'm sure there are other ways. So this is your start point. But if the environment gives you flexibility to start from a separate point, you start it from, say, here or here, right? When you do that, the policy should later figure out that it has to go like this or it has to go like this. So in doing so, you're sort of telling the policy, you're giving the policy sort of more experience in other parts of the state space that it hasn't visited, so that it at the end goes to the goal. The thing is, this is required for convergence because the value function is defined across all the states, right? So that is why we so the thing is, this doesn't happen, or this sufficiently often part of every state being visited doesn't happen in practice, as you'll see going along, right? This is just a theorem.
Acha. Okay.
Right?
That means this point is not necessarily that I should follow. I mean, the algorithm should follow, right?
Right. Yeah. But the thing is, it's good. It's always good if the policy visits many parts of the state space, so that it has an idea of what is going on. Like, for example, if you just go here, right? So here, sir gave that there's a diagonal. The optimal policy is in the diagonal band, but sometimes it may so happen that there is this sort of magic state over here, right? state that where, and since this is close to the goal, perhaps just going here would maybe teleport me over here, and that might actually be much better than whatever this band is saying. But you wouldn't know this, or the agent would be oblivious to this if it doesn't even explore this part of the state space. So always a good knowledge of the, or rather sufficient experience in all parts of the state space is desirable. But in problems with very massive state spaces, you cannot really use that. You'll also see in week 11 in hierarchical RL how you can sort of impose your domain knowledge to actually ensure that sufficient areas of the state space are being explored. So that can be done. There are some methods for that. But yeah, this part, that every state is visited sufficiently, that is just a convergence result. If you can show that your algorithm is doing that, then it will converge. That is kind of the idea here.
Okay, as you said, some of this means magic state where one state is basically teleporting to the other state for a shorter path. Can you do you have some example in practical where this happens?
Okay, practical. Okay, so RL is used for game playing. And have you played Mario, the first level? Have you played Super Mario Brothers?
Yeah, Super Mario I played, but that is in a very older version.
Yeah, I am talking about the older version only. Everyone has played the older version. Yeah.
Okay. You are saying some hidden path.
Yeah. So I think there's a pipe with a piranha plant that comes up, right? If you press down on that piranha plant and you finish that level, you are almost, you reach the end part where you're like right next to the flag when you come out of the piranha plant. And you also get lots of rewards, right, over there. So that state space is not evident at the start, because the agent might not, it might be just weird to even think about pressing down on top of the pipe unless you have some knowledge saying, okay, this is a pipe, the pipe has a hole, therefore I can go through it, right? So if somehow you nudge the agent to go there, either by making sure the agent starts from there by having some script that plays beforehand, or rather having, I don't want to use the word yet because you will come to HRL in week 11. If you can set those up, then obviously going through that pipe is a much more optimal. That's probably the optimal policy is what I would say, because you get lots of coins there. There are ways to resurrect your lives. If you're not familiar, there are some hacks to actually even pass through many levels. There are glitches there as well. Yeah. So, but point being that these things are always there. So having a bigger context of the state space always helps for it to get optimal policy. So yeah.
Okay. Got it, sir.
All right. Great. Yeah. So in RTDP you don't do that. If I recall correctly, like you don't visit most of the. Yeah, I'll have to confirm that. But yeah, so that you can do. The thing is, you sample more from whatever real time, right? So whatever agent you're following, you are doing RTDP then while following the path to do the updates. So instead of going through all the states like in this loop, where's the loop? Yeah, instead of doing this part, right? Instead of doing that, the order in which you do it is simply based on the manner your agent visits states. So that is how RTDP works. And yeah, value iteration revisited. If policy violation is stopped after one update, yeah. So this is the same thing again. Generalized policy iteration. This is the important part. So even further, you will learn methods like TD learning, Q learning, SARSA. All these things do some form of GPI. So this is something important to understand. All of these is some variant of policy iteration, right? So you let the environment interact using some exploration strategy like epsilon VD, softmax, UCV, whatever, and using the interactions, you internally somehow are maintaining one, your value function, and two, how you are improving it. So in value-based methods, we saw that, right? How that thing is there. So it is made, you're sort of interleaving the evaluation and iteration part, but you can do it in a much more granular level also. So, and almost all RL methods come under this sort of scheme of this paradigm of generalized policy iteration. And the result is this. All these RL methods, that, and there are results that says it converges if almost most parts of the state space are sufficiently explored. So that's the result. I think there was more, right? I think Monte Carlo was also there. Yeah, any doubts so far? If not, I'll just give me some time to get that PDF as well.
No. So, yeah.
Okay. Yeah, Monte Carlo is there. It's not in the. Okay, it's in the week 5 PDF. Let me just get that. So, yeah. Okay. So this is the fifth one, and yeah. So this has Monte Carlo methods. So this was dynamic programming. So in dynamic programming, the idea is you bootstrap. So to get, since the nature of RL itself is to just get this reward part, you don't know the nature of, like, in RL, right? So you get a reward here. Yeah. So you get a reward, but it doesn't span all the way to the end, at least whatever the feedback you get from the environment, right? So therefore, the idea in DP is to bootstrap, which is use the value of this and then the reward also obtained to refine your estimates of the value function. So that's in DP. What you do in Monte Carlo is more straightforward. Yeah, it's straightforward because you run out the entire thing from start to end, and then whatever final return you get, GT, you use this part to update all the states along this path. Yeah, so you directly sample from episodes. You're not bootstrapping it from the sort of the child nodes, and yeah, and they are just, other than that, the GT form everything is same. Yeah. Monte Carlo prediction, you have first visit MC and you also have every visit MC. Yeah, before I move on, can you guys tell me if uh, which one of these is biased? Is it first visit or every visit?
Actually,
Every visit.
this is not there in week 4, right?
Oh, it's there, right? So okay, the how I see it is week 4, yeah, DP value iteration, more on DP. I think, yeah, more on DP we finished. Yeah, this is Monte Carlo methods. Yeah, so there is L4.3 is Monte Carlo methods, and L4.4 is comparison of DP, MC, and TD.
Okay.
Is this not?
Okay.
It's there, right? Okay, great. So Aryan, you said every visit is biased, is it? Okay, yeah, that is true. Yeah, we'll also come back to why that is the case. But yeah, I'm just going briefly through this. I think the professor does a better job at teaching these concepts. The hope is when I go through these things, you guys can come up with doubts, whatever you might have at that point. So in first visit MC, you like, since if you're given a trajectory, from that trajectory onwards, you calculate your return. Suppose once you calculate the return, you update that in your current existing thing. Yeah. So VS is just average of returns. So you maintain this returns list for every VS, and then you just get the average of those and put it there. Bootstrapping, yeah, you have DP that bootstraps, and Monte Carlo does not bootstrap. It's the opposite in that sense. And in sampling, Monte Carlo samples, DP does not sample. What does this mean? Can someone tell me what this means? Is there sampling in DP? The thing is, yeah, it doesn't sample because if you want to do DP, you need the model, you need the information of the model, you need the transitions, you need the policy pi you anyways have, right? But you also need to know the states, the underlying states in your MDP, the underlying transition function in the MDP, and so on. The reward distributions, all that you will require. Only then can you even write the Bellman equation in the first place. If you can do that, then you use DP methods to bootstrap and then further solve. So that was the policy iteration and value iteration, right? In Monte Carlo, you don't have access to that, but you have access to a sample model. In the sense, if you take a policy and what is the sample model? The sample model is just the environment. If you take your policy pi and then run it on your environment, then for every time step you're going to get some reward. And yeah, so your environment is basically the sample model, and then you can use these rewards and do whatever you want. And Monte Carlo does that. Given a policy, just lets the policy play, and then gets the returns, and then updates its original value. So that's why that's what it means here by sampling. And yeah, so this is that map. So DP does full. Yeah, yes, Monte Carlo has deep backups because right from the end to the start, you're doing a backup. Whereas in DP, it's just full backups. Yeah, I'm not sure. Sample backups, yeah. So Monte Carlo samples, and the sampling is deep because it changes the value across for every state it visits. It changes. In TD learning, you'll see that won't happen. In DP, there are shallow but full backup. Shallow because it just bootstraps from its adjacent state. And yeah, that's what it means. Bootstrapping and sampling. Bootstrapping, update using an estimate. Yeah, so which is the adjacent ones. Quite repetitive. Sampling, Monte Carlo and TD sample, DP does not sample. Okay, I hope TD is marked red because it's not covered yet. Yeah, this is the final video in the week. Okay, let's not go there. That's week 5. Any further doubts here? I'll again go through first visit and every visit. No doubts so far, right? Yeah, okay. So, does he have an example here? Yeah, we just get this. We write it more legibly. S2, A2, R1, S1, A1, R2, S3, A1, R4, S4. Okay. Okay, all the states are also unique here. Okay, let me just put this as 1. Okay, so now in first visit, suppose we'll think about updating the return for S1, right? So there are two possible ways you can uh, do this. So one is, since I've seen S1 here, I will calculate the return I get this point onwards. So which is the return from S1. So that would be R2 plus gamma R4. Yeah, this is the terminal state, right? So that would be that. But you see that there's another S1 here as well. So another valid sort of return is this, which is R4, right? Now the thing is yeah. So this is every visit. In first visit, you only take this. Only take this in first visit. Now, why is this biased? Any idea? Yes, Sarin, I'll come back to bootstrapping after this. Yeah. So this R4 that we've received here comes from some distribution, yes, but it we are using it in two sort of fragments, right? So we are using it in both this and this. The if you use first visit, you're sort of reducing this sort of. In other words, you're placing, it's biased because this sample, right? You sample this just once, let's say, but when you're doing it this way, you're sort of implicitly saying you sampled it twice, right? And you see that this R4 occurs here, but it did not actually occur here. So here we have S1 A1 R2, and here we have S1 A1 R4, right? So when I take A1 at S1, so I've already gotten two different rewards, which is R2 and R4, right? So there seems to be some stochasticity, or there seems to be some randomness associated over there. But here I'm placing, I'm giving R4, even though it was sampled once, I'm giving it the benefit of being sampled twice, and that's why it's biased. Okay. However, it is sample efficient because this is still a valid sample, right? This is still a possible one. It's not. It may not represent in actual probability because we are using it twice, but it is still, however, a valid return. Therefore, the sample efficiency of first visit MC is higher, but however, it is still biased. So that's why we say every visit is biased, and first, yeah, every visit is biased. I think I exchanged that before. Every visit is biased, and first visit is unbiased. So yes, that was that. Bootstrapping and sampling again. So in bootstrapping here, yeah, this one, right? So in bootstrapping, suppose we have these values, this penultimate layer values, we will use the values estimated here to update S. So that's what we mean by bootstrapping. Whereas if you're doing sampling, if you're doing full sampling like Monte Carlo, then you completely unroll a policy, right? Suppose you do this and you come to this state, then by following this trajectory, you would have gotten some returns and rewards. So you use that return to update the value of this, then to update the value of this, then to update the value of this. For this while taking A1, this while taking S1, and this while taking this action, and then this while taking this action. So that is sampling. So in bootstrapping, you are only looking at your adjacent states, nothing more, right? In sampling, you're looking at the entire sort of trajectory. The balance between these two comes in TD. And then yeah, you saw the simplest TD method and so on, right? If you go there, you can see how you can sort of choose some particular level between bootstrapping and sampling. So that can also be tweaked, but that comes in TD learning. So yeah, so that is that. Hope that was clear. Yeah. So in Monte Carlo, what did I do here, right? So I drew a complete episode. You roll it out until the end, and then use that return to update this, and this. You're not using these to update this. Remember, you're only using the samples from this entire trajectory to update the state values or the Q values, action values, across all the states encountered in this trajectory. So that is sampling. Hope that's clear. Any further doubts?
So in two method,
This Monte Carlo method, huh?
yeah, means Monte Carlo or bootstrapping,
Mm-hmm.
where the convergence will be fast.
Oh, in when you compare it with DP and Monte Carlo, is it?
Yeah, yeah.
Hmm.
Or it will depend the architecture of the space test.
State space. I cannot comment on. Okay, so yeah. So obviously the answer would be the second one, depending on the state space. Especially like if you say that your environment is, yeah, I'm just putting my thoughts out there. None of this is necessary to be true, but if your environment were completely, not stochastic in terms of rewards, one, and in terms of two, if you're doing an action and it ending up in some state, if it's not like that, then ideally your one sample in Monte Carlo should be good enough to update all your states, and after that it need not even change as much. So if you could somehow make a policy that goes through all of these just once, right? So it explores all of these paths just once with this sort of, obviously it's a bad idea, but with this additional knowledge of the environment not being stochastic at all, right? You are getting the true returns. So here you're just doing an exhaustive search. I think that was here, right? Yeah, that should have been here. Yeah, if you're just doing an exhaustive, yeah, that's basically exhaustive search, where you have both full backups and deep backups. Yeah, that is that. But other than that, yeah, I would just say it's dependent on the environment, because if you're doing DP, unless you do RTDP, no, unless you don't do RTDP, which is evaluated on the entire state space, if the state space is just too huge, then it's probably hopeless for dynamic programming, because there's a lot to solve if given you have access to the model. Whereas in Monte Carlo, if your environment is just simply too stochastic, then you would have to keep taking lots of samples until your thing converges, because you can see that there is big magnitudes of conditioning. So there are many samples you take, and there are many new distributions per se. So if you're doing Monte Carlo, then do you need to get lots of samples for it to converge, and sometimes it need not converge at all. So I think that is also covered, and therefore it becomes important for you to look at methods that strike a balance between these two things, which is where TD learning and TD lambda methods come into play. Yeah.
Okay, means this TD learning or whatever new method will come in forward, means those are basically balancing
Correct.
these two.
Yes, correct. So you can do both at the same time. You can sample and bootstrap. So that's what TD learning is.
Mhm.
Yeah.
Because from the diagram, what I am seen, because this is a very two typical data structure. One is breadth for search and one is depth for search. Look like
Ah,
searching
okay.
algorithm.
Right, right. Uh-huh.
And now we are
Uh,
basically balancing between these two search
yes, so that would be
to.
like iterative deepening search.
Mhm.
You could say that, but yeah, I would not. So those are, yeah, perhaps, yeah, I cannot comment more than that, but yes, so yeah, I kind of get that idea. I would see that. Okay, great. Any further questions?
No, maybe next week we would
Yes, next week
learn
is a fun
something
week. Yeah.
interesting.
Yes, yes, yes. Next week is quite fun. What is there? Uh, yes, TD, MCO TD, SARSA Q learning of policy. Okay, you will look at TD lambda on week 6. Yeah. Week 5, you have TD learning methods. Yeah, that's quite a heavy week, which Swarnim sir will cover in the next week. Yeah. All right then.
Okay. So next week, do we have the week 5 discussion or quiz discussion, sir?
All
So
right.
next week it will be a revision session, and week 5 will be conducted some other time.
Next week is a revision session, right?
Right.
Okay.
Wait. No, wait. Week 5 is you have 23rd, right? The exam.
23rd, yeah.
Yeah. So 22 will be the revision session. Next week it will be the usual session.
22 will be the revision session.
Yes.
But sir, 23rd exam, 22 evening